Hello, everyone. My name is Kevin, and welcome back. Today, we're going to be going through another data structure, and those are Fenwick trees. So, Fenwick trees are most commonly going to be used to find prefix sums. So, what does that mean? Let's say we have some array with a bunch of different values, and I want to find the sum of the first n elements. So, let's say the first four elements. So, if I want to find the sum of the first four elements, I would kind of just add up these four things. So, that'd be 2 plus 1 plus 8 plus 10, which is going to give me 21. Another form of a prefix sum that's going to be a bit more complicated would be, let's say I wanted to find the sum from like 5 to 7. That's going to be 6 plus 10 plus 7. So, I could just add up 5 plus 6, the values at 5, 6, and 7, or I could kind of do the values from 1 to 7 and subtract the values from 1 to 4. And that would also give me the sum of 5 to 7, because I'm taking the sum of the first 7 items and taking out the parts that I don't really want and focusing just on that magic sum right there. Okay, so with that in mind, there's going to be two main approaches that you might naively take to solve this prefix sum question. So the first would kind of be to have a constant time update. So that would just mean we have an array, just like this one. And let's say I said I wanted to update the value at the eighth spot, then I would just, go to the eighth spot and update it. Boom, update all of one, super simple. But then if I would want to find the sum, at any point I would have to add up to n values, right? If I want to find the sum of the first eight things, then there's no shortcut. I have to add up the first eight things. So it's going to give us an O of n sum technique. Okay, not terrible. Can we do better? So your next thought might be, well, what if we save the sum some way? So we get the sum in O of 1. So this would mean that we have another array with, sums in it. So maybe the first spot would have 2, the next spot would have 3, next spot would have 13, then 21, and et cetera, et cetera. And we just keep storing all these sums super condensed. However, though that will be able to give us the sum in O of 1, our update is going to become O of n. Because if we want to say we tweaked the value that would be at our first spot, well, we would then have to update every single one of these sums down here in our new array, which is going to be quite slow. Okay, so with our naive approaches, we have, two different things that we can do, but we're always bounded by something being O of n. And Fenwick trees is just a clever way that allow us to mitigate this O of n step, putting both of our update and our sum into logarithmic time. So how would we do this? So you're going to notice that I have this array right here, and that I did something weird where I one index instead of starting from 0. And that's going to give us some cool math tricks that are going to allow us to form a Fenwick tree. So let's try and build it out. So kind of the methodology that we're going to start with is how can I store all these sums with the least information possible? What does that mean? So let's kind of think about things in power of two for a second. So if I, have a value right here that I'm going to store separately, and that's going to take the sum of that first element. So for all these boxes I'm going to draw, we're storing it at the index where the last line ends. So it'd be like at the first index right here. And we're going to add up everything from here to here. So to be a little more clear, let's also take a sum of the first two elements. We would store this sum right here at index 2, and add up element 1 and element 2. Let's just keep going through these powers of 2 for a second. What about the first 4 elements? A little messy, but there you go. Let me redo that. First 4 elements right here. Okay. We have another sum. It's going to be stored right here at the 4th index, and it's going to hold these 4 values. And if we keep going through these powers of 2, we're going to get another one with our first 8 values right here. Not bad. And another one with our first 16 values. So at this point, if we kind of just cross off all the spaces in our array that we filled this one, this one, this one, this one, and this one. Okay, not bad. But there's definitely some gaps. So now we're going to try and fill in these gaps, and the value that we want to fill them in is going to allow us to compute every possible sum. So what do I mean by that? Let's focus in on these first 4 values right here. So if I want the prefix sum of the first value, I can get that. First 2 values, I can get that. And I can't really get the first 3 values. I can get the first 4 values though. However, if we kind of think about this, we don't know what this value is right here. We don't know what the value is right here. But we do know what this sum is right here, because that's going to be this value minus this value will get us this value. So all we really need is if we can already can determine this value, if we have either this one or this one, then we can determine this whole value. So we're just going to add one sum, and that's going to be right here. And just like that, I'm now storing every possibility within the first four values. Okay, let's kind of do this a bit slower. So what we're going to do is every time we find a gap, so our next gap is going to be right here, we're going to try and put something of size 1. So this sum right here is going to store only the fifth value in it. And then now, let's try and do something of size 2 as well. Okay, so now if we fill in all the spaces that we'd have this one, and this one. So our next thing would be to try and put something of size 4, which would be like this. And there's no need to put something of size 4, because we already have something in this space right here. We're going to head over to our next gap, and we're going to put something of size 1. And if we tried to put something of size 2, again, we wouldn't need that. There's already something right here. So now with just 1, 2, 3, 4, 5, 6, 7, 8 boxes, we have filled in our first 8 spaces, and we're able to get every possible prefix sum out of this. So let's say I wanted the prefix sum of the first 7 elements. Well, that's going to be this box plus this box plus this box. If I wanted the first 6 elements, that would be this box plus this box. First 8 elements, that's just going to be this box. Okay, starting to get interesting. Let's just continue going through this pattern. I'm going to go a bit faster. So we just need one box right here. Then we can fit in a box of size 2 right here. And we can fit a box of size 4 right here. We can't fit a box of size 8 because there's already something all the way down here. So now if we fill in our gaps, we have this one, and this one. So our next gap is going to be right here. So we're going to add a box of size 1, and a box of size 2 can't fit because we already have this space filled. So this is done. So if we head over to our 13th index, we can put a box of size 1, box of size 2. We can't fit a box of size 4 because there's already something all the way down here. So we're just going to add another box of size 1 right here. And we can't fit a box of size 2 once again because there's going to be something right here. So just like that, everything is filled in. And if we just do what I said before one more time, let's look at these boxes. If I wanted to put something, get the sum up to the 14th element, that's going to be this box, plus this box, plus this box. And we can see that just like that, we're getting every element within the first 14 steps. So is there a mathematical reason that this is happening? And if you happen to ask that, you would be right. Let's look at the number 13 real quick. So 13 in binary, well, that's just 1101. Okay, and let's just kind of remove our least significant bit for a second and kind of separate it out. That would be 1100 plus 0001. And let's just do that one more time. That's going to give us 1000 plus 0100 plus 0001. And if you know your binary, you can see that that's kind of something like 8 plus 4 plus 1, which adds up to 13. But if we go look at 13 real quick, look at that. 1, 4, and 8. We add up the elements that relate to each of these bits individually. So that's going to be kind of our algorithm. For any of these numbers, let's do 10 next. So 10 in binary, that's going to be 1010. So we're going to need to add up, we're going to start at 10, and our first sum is going to be of size 2, because our least significant bit right here is going to be in the 2 spot, and our next sum is going to be of size 8, because our next least significant bit is in the 8th spot. And that's why we had to start from 1 right here. Because let's say I started from 0, and I was trying to find this prefix sum. Well, there is no least significant bit. So by starting from 1, we guarantee at any point that we have a least significant bit that we can call on. So let's kind of start drawing this out in a different way. If I take this right here and I kind of flip it on its head, we're going to see something that starts to resemble a tree. So let me just draw that out real quick. We're going to have this big box up here that's going to hold like all 16 elements. A smaller box, sorry, it's not going to be perfectly spaced, but here's 8 of them. Box right here with 4. Box right here that kind of goes 9 through 12. And this is just going to keep splitting up as we go down the tree. And look at that. Okay, so now how would we turn this into a tree form? It's going to be pretty much exactly what you'd expect looking at this. So we're going to form a binary tree. And as we draw out this binary tree, you're going to notice because of what's going on with that 16, it's not going to be perfect, it's not going to be full, and it's not going to be complete. But if we neglect that 16 and just look at everything else, it's going to start looking like a perfect tree. And it's going to get a bit messy right here, so sorry about that. And that is that shouldn't be surprising. And the reason why is if we look at this drawing right here, everything is kind of coming in these groups of threes. 2, 4, 6, 10, 12, 14, 4, 8, 12. And the only thing that doesn't come in this group of 3 is 8, 16, and something, which is why there's this gap right here. And if we continue building out this tree, more stuff would populate over here. And eventually it would keep going upwards, and there'd be a lot more stuff over here. This is, the sum of the first 16 elements, and this is the tree that manifests. And this tree, if we continue looking at things in terms of binary, is going to have a lot of interesting properties. Let's look at this bottom level. 1 in binary is going to be 0, 0, 0, 1. 3 is going to be 0, 0, 1, 1. 5 is going to be 0, 1, 0, 1. And now I'm just going to fast forward to 13 again. It's going to be 1, 1, 0, 1. And 15 is going to be 1, 1, 1, 1. 8 plus 4 plus 2 plus 1. And everything at this last level, if we look at the very last bit, it's going to be the same. They all end in 1. Now let's look at the level above it. 2 is going to be 0, 0, 1, 0. 6 is going to be 0, 1, 1, 0. 10, which is our next thing, is going to be 1, 0, 1, 0. And 14 is going to be 1, 1, 1, 0. If we look at the last 2 bits of everything on this level, once again, they're all the same. Let's do this one more time. We go to the level above it, 4, 0, 1, 0, 0. 12, 1, 1, 0, 0. On this level, the last 3 bits of everything are exactly the same. Interesting. So this means that we kind of built our tree right. So, at any point, if I want to get my prefix sum, I go to that index, or I go to that part in the tree, so like the 12th spot in the tree, and 12 is this right here, and we're going to do that algorithm, where we're going to get that sum right there, we're going to remove that least significant bit, which is going to bring us up to 8 right here, and we're going to add up 8. And if you remove that least significant bit from 8, we just end up with 0, we're done. 13. We start right here, we add it, we remove that least significant bit, so that's going to give us the 12. So it's going to kind of go up the tree, head over to 12, and we're going to add up 12, remove that least significant bit, head up to 8, and repeat. Let's just do one more. 7. 7 in binary is going to be 0, 1, 1, 1. We're going to add up 7, which is this box right here. We remove that least significant bit, and we get 0, 1, 1, 0. So we have to add up 6. So far for 7, we've had to add up this one and this one. From 6, we're going to remove that least significant bit. So we're going to end up with 4. We add up 4. So now we've had to add up this, and this. And look at that. When we remove our least significant bit from 4, we're down to 0 and we're done. So just like that, the worst case we're going to have, as you can see from all this, is to go all the way up our tree. And if we ignore 16, then this right here, we just said was a perfect binary tree. That means that there is going to be at most log n levels. I mean, on this part of the tree. So our entire tree is going to have at most log n plus 1 levels, which means if to get our sum, we just have to traverse up the tree, it's going to be O of log n plus 1, which is going to be bounded by log n. So to find the sum, we've now done this in logarithmic time. Yay! Okay, what about updating? Because updating is going to affect our entire tree. So let's just go back to this picture for a second up here, or let's look at this one. And let's look at 13 again, because it's a nice number. So if I update 13, what else is going to be affected? Well, if I change this value in our array, this one right here, that's definitely going to mess up 14. It's not going to mess up 12, because 12 stops before 13. It's going to mess up 16 though, for sure. Let's look at some other things. Let's look at 9. If I want to update the sum at 9, it's going to mess up 9. It's going to mess up the one at 10. It's going to mess up the one at 12. And it's going to mess up the one at 16. So basically, if we're looking at this picture, if I update any one value, if we just kind of draw a straight line down, we can see everything that could get messed up. So what does this mean in a mathematical sense? Before we get there, let's just kind of see if we can fake it, see if we can figure out what this algorithm is going to be. So for 13, we just said that if I mess up 13, I would have to change 14 and 16. So this one, and this one. We also just said if I tweak 9, it would be this one, this one, this one, and this one that we have to update. So just from that, you can kind of see that all of these follow going parent to parent. If I tweak 9, then the only thing I would have to touch are its parent, its grandparent, its great grandparent, or its great great grandparent, etc., etc. And that's actually going to be true for everything. If I tweak 5, the only possible things that I could have to change are all going to be traversable directly up the tree. But how do I determine if I go up the tree, which ones I need to tweak or not? So we just said for 13 that we would have to tweak 14 and 16. And what do 14 and 16 have in common that 8 and 12 do not? Well, 14 and 16 are both bigger numbers than 13. So if we want to just create a general algorithm, it's going to be just keep going up the tree. If the index at that spot in the tree is bigger than the index of the thing that I updated, then we're going to need to update that as well. Otherwise, just keep on rolling with life. So 14 is bigger than 13, we update it. 12 is less than 13, we don't update it. 8 is less than 13, we don't update it. And 16 is bigger than 13, so we will update it. So mathematically, what's happening is if we look in binary again, 13 is representable as 1101. So if we take the value of the lowest bit, that's going to be just a 1 right here. So we're going to kind of add 1 to 13, and that's going to give us 1110. 14. Okay. If we look at the lowest part of 14, that's 10. That's 2. If we add 2 to 14, we get 10000, which is 16. And that's actually going to be a pattern that's going to follow for everything. So let's go back to 9 for a second. 9 in binary is going to be 1001. If we add 1 to that, which is the value of our least significant bit, we get 1010. 10. Okay. Let's add 2 to that. That's the value of our least significant bit. So that's going to be adding 1 0 to that. That's 1 1 0 0. Look at that. That's going to be 12. And let's add 4 to that, because that's the value of our least significant bit. And we get 16 again. And if we look at this tree, 9, 10, 12, 16. That's everything that we have to tweak as we go up. So just like our sum, the only thing we have to do is, go up our tree. So once again, our update is going to be bounded by log n, because that's, our worst case. So we have to go all the way up the tree. Okay, awesome. That's going to be about wrapping it up for Fenwick trees. Thanks for watching.